So today we'll be finding the electric field at the origin that's created by Q2 and Q3 in the vector form, and then we'll also be finding in vector form the force that Q2 and Q3 have on Q1. So we'll start with the first part, and we do have our formulas right here. And we do see that the force of, well, this will just be our point. So we'll ignore it being positively charged for now, but at this point, our force of 2 at our origin, it will only have an x component. And then we can see that the force of 3 on our origin will only have a y component. So, these will be two separate equations, and we are looking for the electric field, so that will be this equation. And we will start setting it up. So we have our electric field in the x direction, and we said that the x is our Q2, so we have our Coulomb constant times the absolute value of 5.5 times 10 to the negative 9, because that's what the nano is. And then it's divided by r, and r is the distance between the point and the charge, and we have it in meters, so that's perfect. We have 0.3, and then we square it. And then we will set up our equation for the y direction, and we said our y direction is 3 on the origin, so we have our Coulomb constant times the absolute value, so we can take off that negative and just put 3 times 10 to the negative 9 all over the distance between the charge and where we're calculating the point. And we have it right here, which is 0.1 meters, and then squared. And once we do the calculations, we can remember that our Coulomb constant is 8.99 times 10 to the 9. Once we do our calculations, our x component, we should get 549.39. And then for our y component, we should get 2,697. And then this one is our I hat, and this is our j hat. But remember, these are just the magnitudes, and as we can see, from just a point right here, ignoring that it's a charged particle, we know that our positive electric fields will be radiating outward, so on that point right here we will have a force going this way from Q2, and then on Q3 we know that if it's a negative, it will be pulling it inwards, like in towards the center, so our y will also look like that. And when we take the magnitudes into account, we will have a negative 549.39 for our I hat, and then our j hat will also be negative 2,697. And that is the first part of our question. So I will erase this since we got that done. Oops. We'll put that one back. Okay, so for our next part of the question, we will be looking for our vector force, and we do know the equation equation for vector force is this one, and we will be finding it on our Q1. And our Q1 is 5 nanocoulombs. And just to do this again, we do know that we will have an x and y component of this. So now we can start with a little free body diagram of our Q1 particle, and we know that Q2 is also positive, so that means the force will be going this way, be pushing it away, because they are like charges. And then we do also know that our y component with for the Q3, they're both negative, or they're both different charges, so they will attract each other, meaning it will have a force going up this way, and we can label them force of 3 on 1, and then this one can be the force of 2 on 1. And we can just start plugging our stuff into the equations real quick. So we'll have our electric force of 2 on 1 equals our Coulomb constant times our charge 1, which is 5 times 10 to the negative 9 times the magnitude of our second charge, which for 2 on 1 is 5.5 times 10 to the negative 9, and then we divide it all by the radius, or r squared, which is also the same distance between the two charged particles, the perpendicular distance, which is 0.3, and then we square that. And then for our y component, our force of 3 on 1, we will get our Coulomb constant times our Q1, which is 5 times 10 to the negative 9, and then the magnitude of our second charge, which is magnitude, so it's 3 times 10 to the negative 9, and then we divide that by the distance, and we can see that it is 0.1, and then we square that. And the answers that we should get once we calculate them, in our x direction, we should get, so since we are just finding the magnitudes at the moment, we should get 2.75 times 10 to the negative 6. And then in our y, we will get 1.348 times 10 to the negative 5. But we do see up here that we want it in microcoulombs, or for our exponent, we want it to be a negative 6. So we will just move the decimal one place, and then we get 13.48 times 10 to the negative 6. And remembering that these are just the magnitudes, we can go back to our free body diagram and look at what our signs would be. So for our x, we do see that it is going to the left, so that shows us that we will have a negative 2.75 there, and then our y is going up, which is positive, so we will have 13.48.